Welcome to The Explainer. Today we're uncovering the hidden mechanics of commercial air travel. You might think you know exactly what's going on when you buckle up for a flight, but the physics happening behind the scenes, and honestly, the intense economics driving them, are absolutely fascinating.
Okay, let's dive into this. Seriously, why do you actually have to put your phone in airplane mode? And could a rogue passenger realistically just pull the handle and open the emergency door mid-flight? These are easily two of the most common anxieties and really persistent myths surrounding air travel. And to get to the bottom of them, we've got to look up, way up.
To deeply understand the physics here, we first have to talk about the money. If we break down the fuel burn during the different phases of a flight, climbing burns a massive 80 kilograms of fuel per minute. At first glance, that seems like a total waste of energy, right? But once you finally hit cruising altitude, that fuel burn drops right in half. And descending? Well, that's almost negligible. It turns out that huge initial burn is actually the catalyst for a brilliant chain reaction of long-term efficiency.
So why is that? It all comes down to one staggering number, 73%. When an airplane climbs up to 33,000 feet, the air density drops to just a third of what we have down here at sea level. Because the air is so incredibly thin, the plane runs into only a fraction of the air molecules it would closer to the ground. This means the aircraft can fly 73% faster using the exact same amount of thrust. You get to your destination way faster, and because you're spending significantly less time up in the air, the airline ultimately burns way less fuel. And this altitude advantage, it's totally compounded by how jet engines actually operate. They rely on three basic steps. They compress intake air, they mix it with fuel and ignite it, and then they eject that incredibly fast exhaust right out the back. What's absolutely crucial here is that this whole combustion process is drastically more efficient the colder the air is. Up at cruising altitude, the temperature sits around minus 50 degrees Celsius. So flying high isn't just about reducing drag. It literally means burning less fuel for less time, all while neatly avoiding most of the weather and turbulence down in the lower troposphere.
But here's the catch. This purely economic decision to fly high creates a deadly biological problem for us passengers. Up at 33,000 feet, while the air still technically has 21% oxygen, the atmospheric pressure is only a quarter of what it is at sea level. The partial pressure of oxygen drops so incredibly low that not enough molecules can force their way into your blood. If you're exposed to that unbreathable air, you'd pass out in about 3 minutes flat.
To survive up there, airlines have to continuously pump compressed air into the cabin to pressurize it. And this basic human need forced a radical, totally genius redesign of airplane doors. Before pressurization, planes flew lower, and the doors just opened outward on simple hinges. But now, planes use a plug door. It's a clever design where the door is physically wider on the inside than it is on the outside. The high internal cabin pressure forcefully pushes the door outwards against its frame, locking it in place and creating a perfectly airtight seal. And this brilliantly illustrates why you never need to worry about someone opening the door mid-flight. Because the pressure difference between the inside and the outside is so extreme, the door is essentially wedged into place. To pull that inward swinging door open at cruising altitude, a passenger would need the pulling force equivalent to lifting 9,000 kilograms. No way. It is completely physically impossible for a human being to force it open.
Now, airplane cabins aren't actually perfectly pressurized to sea level pressure. At cruising altitude, the cabin pressure is allowed to intentionally drop to about 77 kilopascals, which gives us just enough oxygen to function totally normally. But the slight pressure drop has some very quirky side effects. Have you ever noticed your bag of potato chips inflating like a balloon mid-flight? Yeah, that's the lower cabin pressure at work. And because the gas inside your body also expands, just like that chip bag, well, let's just say passenger flatulence increases significantly in the air. The gas expands and it has to go somewhere.
But you might be wondering, why not just pressurize the cabin perfectly to sea level? Just like the International Space Station does. Well, think about this quote: stretched and relaxed, stretched and relaxed. The ISS goes to space once and stays pressurized. An airplane, however, climbs and descends multiple times a day. Every single time the cabin pressurizes, the metal fuselage physically expands, and when it lands, it relaxes. Over time, this repetitive motion leads to metal fatigue. In 1988, Aloha Airlines Flight 243 suffered an explosive decompression at 24,000 feet, tearing the roof right off the plane, because that specific 737 had endured nearly 90,000 flight cycles, way more than it was ever designed for. So engineers pressurized cabins to the absolute minimum extent possible to reduce that structural stress and keep the aircraft flying safely for years. Which brings us perfectly to our next big question, the persistent cell phone myth. We're actually still flipping on airplane mode today, largely due to an outdated regulatory history. Way back in 1961, the FAA banned FM radios because they actually did interfere with navigation. Decades later, in 1991, the FCC stepped in and broadly banned cell phones. But by 2005, Congress was explicitly told that mobile phones have never caused an air accident, and today, the EU is actively pushing for 5G in flight. So while the paranoia back in the 90s, well, the FCC worried that a single phone zooming along at 800 kilometers per hour would rapidly try to connect to dozens of ground towers all at once, totally overloading the entire ground-based cellular infrastructure.
But here's the thing. The FCC never even tested this theory. And it turns out the fear was completely misplaced anyway because of a really cool concept called a Faraday cage, a metal enclosure that blocks electromagnetic signals from entering or escaping. An airplane is essentially a giant flying Faraday cage. Your cell signal can't easily shoot straight down to the ground. It's forcefully funneled horizontally out those tiny little plastic windows. Plus, ground towers naturally point their receivers downwards to catch signals from people walking around on the street. It's incredibly difficult for a phone in a cruising plane to connect to a ground network in the first place. Honestly, the most airplane mode does for sure is save your battery from desperately searching for a non-existent signal.
Now, what's really interesting about this is how the physics of flying actively alter our own biology. Specifically, our taste buds. Have you ever complained that airplane food tastes incredibly bland? Well, it's not necessarily the airline's fault. The Sahara Desert has an average humidity of about 25%. Inside an airplane cabin, it can be as bone dry as 5%. This intensely dry air aggressively dehydrates your nasal passages, essentially destroying your ability to properly smell and hugely diminishing your ability to taste basic salt and sugar. But one specific flavor bucks this biological trend entirely. A massive 25% of passengers actually order tomato juice in the air. What's even more bizarre from this German survey is that almost a quarter of those specific people explicitly stated they would never, ever drink tomato juice down on the ground. So why this sudden massive craving for tomato juice at 33,000 feet? The answer lies right there, hidden in our anatomy, the chorda tympani nerve. A fascinating study from 2015 discovered that this specific nerve, which carries taste information from the tongue directly to your brainstem, runs right past your eardrum. The constant, loud, droning engine noise of the airplane cabin physically vibrates this nerve. This constant vibration creates a bizarre audio-sensory illusion that actually supercharges our sense of umami, that deep, savory flavor found in MSG, soy sauce, and yes, tomatoes. The environment of the plane is literally rewiring your taste preferences mid-flight. So this physical environment is incredibly complex, and sometimes the way we learn about it is just as complicated. Take the stark contrast in media coverage regarding flight turbulence. A recent 2023 study suggested a potential link between climate change and increased flight turbulence. Now, notice how some media outlets immediately framed this as a growing absolute danger to air travel, while other outlets painted a completely different picture by simply dismissing the study altogether. When we look at aviation, or really any scientific data, it is absolutely essential to analyze all available information impartially, comparing the actual sources rather than just reacting to sensationalized headlines.
So the crucial point is summarized beautifully by this thought. Every flight becomes a little bit safer. Aviation experts don't just react to the loudest headlines. They constantly analyze every single anomaly. From aerodynamics to pressure fluctuations to pilot reports on weather events, hundreds of aviation professionals are relentlessly digging deep into the data every single day. It's this quiet, objective, constant analysis of both physics and human behavior that ensures nonstop safety improvements across the entire industry. Which brings us right to our final thought. Now that you intimately understand the brilliant chain reaction of physics, engineering, and economics keeping you incredibly safe at 33,000 feet, what other hidden engineering marvels are you interacting with every single day? The world is absolutely full of invisible mechanics just